Okay, hi everyone. This is a different kind of meeting because what we're looking at is some Wolfram Institute work on a Paclet for hypergraph, well, hypergraphs in general. And so Nick was going to show how this works. And this is the first time I'm seeing this. So there's a hypergraph object.
Yeah, so basically the idea is to show first of all, it's the Paclet for hypergraphs. So there is a hypergraph object, and hypergraph object contains some edges and vertices, right? Some additions from previous idea.
It automatically renders like a graph does.
Yeah, it's like a first-class citizen. It has a red border.
How stylish.
Like graphs have like some purplish, trees have greenish, and hypergraphs are red. We decided for some reason. Okay, so one addition that
I would argue, by the way, in terms of that theming, the physics project has traditionally been a purple themed thing, so we might consider that. Yeah. But that's a
graph is already purple, right?
I know. So let's see what purple it is. It's very purple. Well, we should let the design group maybe have a suggestion about this. Okay. All right. So that hypergraph is an ordered hypergraph. Is that correct?
This actually is this is actually, we are dealing with unordered by default. So one thing I will show a bit later, that we have like an additional annotation to each edge, which is its symmetry. And by default, it's unordered. One actually can show it now. Why not? Right? So we can annotate each edge by the symmetry.
I mean, one of the things that we learned in the physics project is the value of having ordered hypergraph structures. The unordered case
also didn't like it.
What's that?
I think Carlos can defend this position more clearly, because I was also kind of against unordered by default at first.
I think it's a mistake. I just think a list is not unordered by default. If we had a set object that was unordered by default, I would be more inclined to say that this is right. But it's a list. It's not unordered.
Yeah. So let me jump in a second. So the reason why we want unordered by default, I mean, this is just a choice. There's not so much of a conceptual preference to unordered or ordered. It's more that we need a control on the symmetry of the edge very explicitly. So we could make them ordered by default, and then they are like the hypergraphs in the physics project. There's no difference there. I mean, it's just a matter of what is default. I mean, that's just an option. But what is different here is that we are giving a very explicit treatment of symmetry. We are.
I get it. So it makes more sense to have them unordered by default with no symmetry, and then to say as the annotation what symmetry you want to have. Because what we've got, if you remember, how permutations work, for example, we can specify yes, exactly like that.
Yeah. But I think what you said is exactly what we have. I think you say that they should be unordered by default.
No, I'm sorry. They should be by default. They should have no symmetry by default. If you want them to have symmetry, put in a symmetry.
Yeah. It's just a matter of what is the default option.
No, I understand, but by no symmetry, I mean that 1, 2, 3 is equivalent to nothing else.
Sure. Yeah.
Okay. But this is the no symmetry because it's ordered.
Yeah.
And we interpret or represent the symmetry by just generators for the permutation group.
Yeah.
Fine. But that's what I'm just saying. I think it's a no-brainer thing that the default should be that there isn't any symmetry. And if you specify a symmetry, great, then you have a symmetry.
Yeah, I mean, here the whole debate is simply whether you take lists or you take multisets as your default.
I know, but we have lists.
Yeah.
Lists are the thing that are, and plus they turn out to have worked rather well in the physics project. So I think we should, we shouldn't go against that. This is a minor thing.
Yeah, it's a minor. It's just a choice. It's not.
So that's an easy thing to fix.
Let's
move on.
Sure.
All right.
Is it the right thing to use an annotation for the symmetry? Or is that actually more of a serious construct? I mean, in other words, we don't have the notion of a list, in the language, we don't have the notion of a list with a certain symmetry, but we could have. We certainly have the notion of a structured array with certain symmetry.
Yeah, and like tensor symmetry is symmetric and asymmetric.
Right. So I think we should be
But
using
here,
that in some. Go ahead.
But here, I don't know, just much easier for now. Just store every additional concept, like an option, as an annotation. Just model graphs as much as possible. It's like I support a bunch of those annotations.
Fair point.
So
that's a fair point. By the way, Jonathan, hello, Jonathan. Do feel free to jump in.
Yeah, sorry, I tried earlier, but I think we moved on, so it's okay. I'll jump in again if it's relevant.
Well, did you want to re-jump to whatever you were jumping to before?
I mean, I just had a couple. I broadly agree that particularly if you're representing symmetries as kind of subgroups of the permutation group, then it makes sense to have no group structure as the default. Although to play devil's advocate a little bit, I do think there is something inherently a bit weird about the fact that you've got a nested list. The outermost list is orderless, but the innermost list is ordered by default. That's the one that's the strongest defense I can see for this.
Yeah,
structure.
right. I mean, we've had that issue, in everything in the physics project because we are currently treating sort of hyperedges as being a big vat of hyperedges and not an ordered sequence of hyperedges. That's what we've got.
Right. I mean, so.
Yeah.
I mean, the only thing I can add to that is that, yeah, so this is exactly as Nick says, this is precisely a problem that we run into when doing tensor algebra. So right now, for instance, in the symbolic representation of, things like Riemann tensors and stuff, we essentially use the same structure that you've got either a list or a sparse array. And then in that case, it's not an annotation, but it's just a kind of effectively a list of slot symmetries. And then you have to do, complicated Butler-Portugal algorithm.
How are the slot symmetries stored?
So it's a list of rules. Effectively what's going on internally is it's modeled on what we did for findable from a model proof, which, this is, the sort of hypergraph theorem prover, where you say what's effectively going on, you sort of algebratize the whole thing so that the case of an orderless hyperedge or something is the case where the composition operator on the individual hypervertices is has a commutativity property. So you reduce everything to some algebraic axioms. And then, right. so in the case of the tensor algebra stuff, there's just a list of algebraic axioms that say, what the symmetries of the Riemann tensor are or whatever.
But how does, I should know this, but how does a structured array, we have symmetries for structured arrays, don't we? Nick, do you know this?
Well, I only know that for just symbolic tensors.
Array. Just say structured array.
No, I just want to show this like symmetric. Okay. What structured array? There are different structures, right? But for symbolic tensors, I know the like special symmetries, like symmetric, antisymmetric, you can use.
Right. But we need to know how those are used because that should inform this. Because it'd be nice to be able to say symmetric for,
no, that might be like I was planning to do something like this for a representation, for a different representation. Right now, we store edges as this incidence list of edges, right? Like for graphs, but for graphs, there's also multiple representations. You can store them as list of edges, or you can store them as an adjacent symmetrics.
Yep.
And if I also will implement this additional representation as a hypermatrix in this case, I can also annotate it with this kind of symbols and symmetries. So, but that's for the future.
We should let you go on here. Okay. So, onward.
All right. So the focus of this Paclet overall is to focus on more smaller hypergraphs, right? It also supports what I was going to mention, like zero arity edges too, right? And there's because we focus on the small edges, there's also a nice widget. Yeah, so we can draw a bunch of small hyper edges very easily now. There's a nice widget for that.
Yeah.
Yeah.
As I think I said before, the fonts are wrong on the right. Just a small point.
No, I think I changed to a different font. Well, maybe to a wrong one. It's a different.
Just use the text font.
The text font?
You don't want to use a code font for that.
Well, maybe because I think I use some kind of Arial or Courier. I don't remember.
Don't use an
But-
absolute font. Just use the text font, and you'll be fine. I
Yeah.
think. And
Wait a second. Well,
I mean,
anyway.
there's probably a little bit of detail in this that could be improved, but this is still very cool.
Yeah, there's like a different modes of drawing edges. Like you can do, instead of selecting and then pressing a button, you can drag and drop them like this. And after you draw it, you can click copy it. Right now we have this object. And you
So
can,
if I say input form to that object, wait a second. What happens if I say input form to that object?
it's a hypergraph. Right, with the hyper edges, a list of vertices, and a bunch of options.
With
Like
vertex
graph.
coordinates there.
Yeah. It's like this. Those
So
are
you've got a
traditional
direct
form.
analog of what the heck is that?
It's
What was
a
that?
traditional form. Traditional form just showing the edges like this.
Huh.
Like it shows
Okay.
here. This is the
Yeah, I
traditional
noticed
form.
that.
Yeah.
Wait. You're just sliding that by. That's a non-trivial and somewhat interesting form. Why is it the right form? I mean, so every hyperedge looks like a permutation or something there. But it doesn't. It's not really a permutation.
No,
Every
just
Could you show it again?
I just replace list.
I know.
with
I can see.
Nothing,
Is that a
nothing fancy.
notation that anybody else uses for hypergraphs?
Maybe.
So
But-
I can comment briefly that the brackets I think is just incidental there. I don't think we ever made a strong choice about that. But the use of the O plus, it's actually operational because we have hypergraph addition and it works exactly as it should algebraically without notation. So that's
cool. I mean, you could then think of a graph as being, some kind of sum like that of pairs.
absolutely that's right. That's right.
And actually, you can add hypergraphs.
Exactly. Yeah, that's the point.
Like
Yeah.
like this.
How? Whoa.
So it's like a direct.
You can add a
union.
hypergraph, but that's, the atom one is the same as in both cases, which is not obviously the right thing. How would I do that? Adding it as two different hypergraphs where, for example, the 8s are in common, but the other vertices are not.
No, then it has to be
gives-
implemented
yeah.
some disjoint union thing. We
Yeah.
don't have a function for that, but it's going to be
Okay.
hypergraph disjoint union or something.
Yeah, basically,
Later.
yeah, it operates like you expect, Stephen. It operates that the common vertices are sort of multi-edge addition.
Yeah, I see it, right.
Yeah, and the spare ones are sort of partial addition over.
So
That's
for a
good.
graph, let's just write out for a second.
Yeah.
For a graph written out as an edge list, could you just do this for a second? Just make a random graph. That's a fairly small random graph. Well, not
Right.
that
Okay.
fine. All right, now let's give the edge list. Okay. So,
Yeah.
right. So if I say join that thing to itself, then I'll just get double edges.
Yeah.
Okay. Fine. Okay, so that's the same thing that you're doing. That's fine. Okay,
Yeah.
I get it.
And maybe Nick, it's a good point to comment on the embedding that is just temporary at the moment. We're using some graph embedding of the projected down hypergraph.
Yeah, I'm still using graph embedding underneath. Nothing fancy. I just also add some dummy edges so that it looks like this, like curved. you
Yeah.
know?
It's
So-
cute.
Yeah,
I
I want to
like the
comment-
way that it works with multi-edges down below.
Yeah, I want to comment that the intention is the ones that look convex, right? Where sorry, concave, the ones that look like spider web. That's kind of the intention, so
Yeah.
that you can have the lower order stuff not get in the way of the higher order stuff, and so visually helpful. But at the moment, it's just using the embedding, so some of them are concave and some of them are convex more or less randomly. But eventually, we want to do our own embedding function for hypergraphs. So the way we're thinking is we're going to take hyperedges so that it's cheaper. We're going to take hyperedges to be always contained in a plane in principle, and then we're just going to orient the planes to display the least intersection and things like that eventually.
What did we do? I mean, so Max had a whole way of doing hypergraph visualization, particularly in 3D. I mean, Max spent a long time doing. Well, I know you have 3D. But do you understand what Max did?
Well, for the 3D case,
we spent a long time talking about. We had a whole crazy scheme. Maybe Jonathan remembers. We had a whole crazy scheme with a bunch of optimizations.
It was generalized spring electrical was ultimately what it boiled down to.
Yeah.
But there was another thing for the surfaces.
Right. So it was spring electrical with surface tension. So the idea was you had spring forces between hyperedges. Between hypervertices, you had electrical and you had electrical repulsion, and then within an individual hyperedge, you would have a kind of surface tension force that would try and minimize its area.
Okay. And is that different from what you're planning, Nick? Or is that similar to what you're planning?
Well, I'm not sure. Right now, I'm doing something similar. For each edge, I also introduce some dummy vertex. If I use graph embedding with some spring electrical, it also would like introduce some tension or whatever. Right?
Yeah, because I mean, you could
additional
make
edges.
Right. If you introduce enough additional edges, you've got a whole surface there. I mean, if you had essentially a triangulation of additional edges, that would be like an approximation to a surface. You're introducing a single dummy vertex, but in principle, I think these look really nice, at least at these sizes.
I introduce a single vertex for each edge, and I also put like directed edges in both directions so that they curve. And then I extract the edge embedding also and drop one of them.
That is a hack, but it's cool.
Yeah, I know. Yeah. And for the 3D, I also apply, because field curve is not longer works, for the 3D case, I also apply some surface minimization there.
Why does field curve not work?
I think it doesn't work for 3D, so it's kind of annoying. So it's like a polygon, and then I do some surface minimization so that it actually can
we should
bulge a little bit.
Ask a question about field curve. We can ask.
Yeah.
Okay. All right. So
all right.
Onward.
Now rules are the most interesting things. Rewriting. Right. So I have a few examples. So rules now are also first-class citizens. Now they have blue border. They're basically represented by input and output hypergraphs. So you can construct a rule by just its input form is like an input hypergraph and an output hypergraph like this.
And the variables here are just numerical things. I mean, there's no, like in writing in the physics project, we tended to use X and Y and things, but could you have any symbols or any expressions?
Yeah, we'll go to that. So here is like left-hand side, the hypergraph is unlabeled, right? So it's basically an unordered edge. So it can orderlessly match against this one in all possible cases, in all possible ways. And because it's not unlabeled, I'll get to it a little bit later. Basically, for this easiest examples first, this can match against this one in 3 possible ways. Or you may say that you can construct this edge in 3 possible ways again. So basically, applying a rule to hypergraph just produces a bunch of information in this association, like an output hypergraph and some meta information that you can use, maybe some for causality data. Right. So it's because now it's just not just like for the Wolfram model case, it's not just a list of edges, but also some vertices. Rules can also introduce new vertices and just 3 vertices without any edges, or remove vertices from the hypergraph as a part of your writing. So in this case, there's no new vertices and no deleted vertices, but if there are 3 vertices like this here that wasn't part of the left-hand side, something more interesting could happen.
But I mean, a standard physics project rule can create new vertices, right? I mean,
well, only wrapped in an edge. It can't create like 3 vertices because there wasn't an idea of a hypergraph as like a graph with no edges, for example, but a single vertex, right? You couldn't make this with a hypergraph.
How is a free vertex different to a hyperedge with a single element?
Well, it is different because
why?
Well, you can use it within rewriting a little bit differently. Right? You can. It depends on your application, but if you generalize enough, you have edges from 0 arity to n arity n, and vertices. You can put edges around vertices, but you also can have free vertices.
Can you give an example of an application area where that's a useful distinction?
Well, I don't have to like come up with it. I'm just can compare it to graphs, and there's no reason to exclude it for the hypergraphs if graphs can.
No, but I think one of the things that's nice about hypergraphs is that sort of everything is wrapped together. It's just a hyperedge.
Yes. So if I can jump in, we have had a few philosophical discussions about this, and it's something that we're actively thinking. So I agree that a one edge and a vertex are somehow conceptually similar. So actually my view and what is behind the philosophy of how we've designed this Paclet so far is that vertices are somehow, some kind of substrate where your hypergraphs are going to live. And the hypergraph data is actually edge data. So unary edge, binary, etc. Right? So the principle here is that, as Jonathan says, we should be treating one edges effectively as vertex information. So that's why we're treating independent sort of free vertices as uninteresting, or we're sort of dismissing that case explicitly, unless they carry edge information, right? That's kind of the idea.
Yeah.
My opinion on this would be simply that a graph is a special case of a hypergraph where the hyperedges are of arity at most 2, and that means you encompass the distinction between the vertex set and the edge set as a special case.
So one example in which this is relevant. There are 2 examples in which this might get relevant. One is multi edges, right, where you want to keep track of multiplicities, and the other is where you're doing something like categorical diagrams rewriting, and then your objects or one morphisms are somehow distinguishable or not distinguishable. Those are the kind of contexts where you might care about those things.
Wait a second. I thought, okay, wait a minute. In the generalization of category theory, well, okay, somebody who knows much more about this, like Jonathan probably does. I bet category theory generalizes, so it isn't just objects and morphisms, 0 and 1.
Well, yes, there are many possible generalizations, but one of the most notable features of category theory is that you don't need to have a distinguished object set, right? Because every object has an associated identity morphism. If you just know the Hom set, if you just know the set of the class of morphisms, you can reconstruct the class of objects. And I think that's really the question here, right? So with a graph currently, if you just know the edge set, it is not possible to reconstruct the vertex set. Now, in my opinion, it's not clear that has to be a fundamental design feature. It's, as I say, it's possible that you could treat freestanding vertices as hyperedges with just a single vertex in them, and that would extend to the hypergraph case beautifully. And that would be more like the category theory case. That the idea being you can always reconstruct the objects from the Hom set.
Yeah, so I completely agree with that, Jonathan. I think what's happening here is more the implementation that we're doing right now treats vertices as this substrate somehow. And then if we were to do things that involve sort of single vertex rules, then we would put a one edge on them to make it explicit, right? So at the moment, for example, I'll show you some examples in a bit where we leave a naked vertex floating specifically to somehow represent that we are rewriting away, but we're keeping the context information in this sort of double push out rewriting sort of language for those familiar with it.
Yeah. My intuition is that this is not a necessary distinction, but we shall see.
Well, for pragmatic perspective, it's still useful, right? It's like in this example, this free vertex can match against free vertices that are part of an edge. If you represent it as a unary edge instead, you have to like wrap your hypergraph with those. It's not very useful.
To decorate it with little edges.
Yeah, it's like it may be as general as it is, but if you just want as general rewriting as possible, why not?
Well, the reason we're seeing this issue is because we only have the notion of edges. We don't have the notion now. Our edges are just, lists of vertices. We could also have a much more deeply nested structure to represent each edge. And then we wouldn't have quite the same story. So I'm saying, we're making right now our edge is a bucket of vertices, but it could also be a nested tree of vertices and so on. Just, it could have structure in the very structure of the edge.
Yeah, that's the point of the symmetry types, the symmetry tags that we have. That the edges themselves will carry some kind of structure. And
I know,
yeah,
but they could have any structure. The
Any
edge in
structure,
general could
yes.
be an expression of any kind.
Yes,
I mean,
in general,
that's
yes.
not what we're doing here.
I mean, what you've just invented there is expression trees, right? If you allow a hypergraph with arbitrary nesting, you get an expression tree.
Yeah, but and there's a, that was the thing. Who was looking at that? Uti was looking at that, looking at kind of compiling everything to hypergraphs, right? Anybody remember that?
Oh, well, I was doing that, and
you were doing
Uti was working with some specific machines like finite.
Oh, that's right. Yeah. Okay. So what did you conclude from that, Nick?
Well, we can
from the compile everything.
Expression trees, sure. Expression trees, you can do rewriting arbitrary expression trees to hypergraphs. And because we're doing in the Wolfram language, because we're doing rewriting with the expression trees, you can turn any rewriting rule on those to hypergraph rewriting.
Okay, maybe you're going to show
and that's how my multi-computational Paclet worked, by turning usual rewriting rules to hypergraph rules.
Right, except it's not actually in past tense, it's actually in the future tense, because it's a Paclet that I know you worked on and I think needs more, needs a future.
Present tense.
It exists. Yeah, okay, fine.
In some state.
All right, let's keep going here. So I think I more or less understand this.
Okay, so that's the kind of motivation for free vertices rewriting. A bit more when you can swap them around. Okay, well, a bit more examples. There's like a highlight rule, highlight rule function that is in the Paclet that also shows what happened during the writing in a more explicit way. Similar how we had in the set replace function, the Wolfram model. So what edge was matched and what was created. They annotated with some red dashed things around. Yeah.
Well, it's not as exciting in this case because everything got red. But if we had a more complicated hypergraph there.
Yeah, like here, because it can match either against this edge or this edge, right? It's either this one turns red or this one turns red.
Yeah.
Okay, hang on. So I'm sorry to take the discussion back one step, but on the freestanding on the free floating vertex rewriting thing.
Yeah.
I think the thing I'm objecting to there is that it seems like if you're going to go for that generalization, then that is insufficiently general, because it seems to me that if you want it to be the case that you can specify, I can rewrite this freestanding vertex to say this edge or this hyperedge. And then that acts within an existing hyperedge, so like that vertex acts on vertex 1 in that hyperedge, on the green hyperedge on the right. Then shouldn't you also be able to define a rule that specifies that partially specifies a hyperedge? So for instance, it says I've got a rule that's acting on ternary hyperedges, but what it does is it rewrites, say, vertex 1 and 2 to something else. If you see what I mean.
Sorry.
No,
could you?
I'm not sure.
So right now what you've got is a rule that allows you to say, I can do rewriting of an individual vertex to something, right? So if we take that ternary hyperedge there, the 1, 2, 3 hyperedge in sort of in light green.
Oh, this one.
Yeah. So then you for instance, that rule could match, say, vertex 1, and it could rewrite vertex 1 into something, right? As it does there.
Yeah.
Yeah.
Okay, but what if we're going to allow that generalization? Which I agree is a strict generalization of what we did in the physics project. Then do we have an argument for not also allowing the generalization that says I can take vertices 1 and 2 in that hyperedge and rewrite those to something? So in other words, I can take any subset of a hyperedge and rewrite that to something. Why are we only allowing rewriting of single elements?
No, but we can do two
It's not a
elements,
single
right?
element.
We can
Well,
do
here it's 2 elements, right?
Yeah,
What
exactly.
What's the difference between in this case?
That's
The same
a
thing.
good question. Hang on, let me figure this out. Well, I guess I mean, ultimately it depends on the symmetry, right? Okay. So,
Yes.
so suppose you had a 1, 2, 3 hyperedge with a cyclic symmetry. Then you could imagine wanting to say, I want to rewrite the pair 1, 2, but not the pair 2, 1, or something.
Yeah, we keep track of that with the
So
symmetry.
you can do it with labels.
Yeah, with the labels, we keep track of that.
Because
Okay.
like free vertices, they don't have any symmetry by itself because it's not
Exactly.
an edge, right?
Yeah.
They can match like in any subset of vertices on the right-hand side, anywhere.
Right. Okay, but so you're right that they don't have symmetries, but for instance, what if I wanted to say specify a binary edge, 1, 2, and I want that to rewrite vertices 1, 2 in that ternary edge, in that ternary hyperedge? Are you saying I would do that using labels?
No, but no, and you would have to include
Well, you have to match
edge in the input, right?
If you want, like, yeah, you have to do something like, what draw some stuff. I don't know.
Yeah, that's great.
So you have an edge, right? You want to match against the ternary one.
Right. Exactly.
You have to make an additional edge. Otherwise, if it's a binary edge, it's never going to match a ternary one, a part of a ternary one.
But then why do we allow a single vertex to match a ternary edge?
Right.
Well, because it's not an edge. It's like it's an exception that we do for free vertices. That's it.
But
Edges have some
why
special.
only for free vertex? I'm saying if you're going to allow that generalization, then surely you need to go all the way, and
Yeah.
you should allow any
wait.
subset
Any
of hybrids
subset to
be-
match any subset.
Wait, yes, I think
Well, it's kind of different.
Nick, I think that what Jonathan is asking here, if you were to match that to a ternary edge, I would simply include the ternary edge in the input, right? So that's part of the parallel matching. So you have to find the ternary edge and the binary edge, and then you rewrite whatever you want, and it's going to find the subsets, as you say, right? But you have to specify the context of the ternary edge that's going to be preserved in the rewriting.
But what Jonathan, I don't know. I think what Jonathan asks is for if I have a left-hand side that just consists of a binary edge like this one.
Yeah.
Jonathan says it should generalize to matching against like part of the ternary edge.
Exactly. Right.
Right. You're allowing for rewriting for your rewrites to match individual elements of a hyperedge as well as the whole hyperedge.
But I think
why
here
not the intermediate case of a subset?
Okay.
Of a
I see the question here. I think the change in perspective here is that we are not considering, like as you pointed out earlier, we can have arbitrary structures as edges, basically. So the structures of inside the edge, we can really look into inside the edge. It's like we're taking this perspective, we're not really looking into the edge unless it's necessary for some computation or some procedure. And the edges are taken as a whole with their order and their symmetry tag, right? And so if you want to specify a part of it, then you have to do some algorithm and then define new edges and then use those edges to do whatever procedure you want. But at the rewrite level, we are only dealing with the hyperedges as primitive elements in the hypergraph object, right?
I'm totally with you on that, and that would be that's the WPP approach. But then I would argue that's logically mutually exclusive with allowing rewriting on individual vertices, isn't it? If you're saying the hyperedges are the first-class citizens, then you can't drill down and extract individual vertices to do rewriting on them.
Well, I mean, the thing here is that we are doing rewriting over hypergraph objects, and the object carries vertices and edges as separate entities, right? I mean, it's mostly the implementation. Okay. Is not so much the mathematical or conceptual.
I don't think I'm not convinced, but let's keep going because we don't need to get hung up on this particular issue.
Yeah,
I just want to add one intuition that I have, so that the rewriting should be intuitive in some way. If I see the binary edge on my left-hand side and there is no binary edges on my target hypergraph, it shouldn't match, you know?
It shouldn't match.
But when I see an input free vertex on the left-hand side and a bunch of vertices, they kind of match, right? Just visually. So
it's a question of point of view, right? And
it's a question of point of view. I agree. Yeah, I agree. It's just a matter of where they are one edges. Yeah.
Let's keep going because I think it will all become a bit clearer when we see what all the various operations are.
Yeah.
Yeah. So here now, some examples with labels, because the way we have labels on the vertices also have some semantic meaning when you do the rewriting. Okay, so by default, there's if this example, if this hyper edge is not doesn't have any labels on it, right? It applies in all possible ways on this one.
I
So it
thought
can
vertex
match
labels
against.
is just a display thing. It's not really changing.
Well, photography is, but here you actually have some meaning, especially when
For
it's
what?
on the left-hand side of your rule.
Wait. Vertex labels, a display piece of functionality, means something for the graph? That's weird.
So it means something when you use them in your rules, okay? And how it is used maybe gonna be explained in a minute.
Yeah, we might need to. I'm also of the opinion that putting it in the labels was a little bit, unstable in my opinion. But I mean, this is, I think, for the sake of demonstration of the purpose, I think is interesting. And then maybe we have to put it in another part of the object. I think Nick agrees, right? Maybe.
Well, you can look at it as an experimental feature. Okay.
Yeah.
Okay,
yeah.
all right.
Labels in the rules.
Yeah.
Just to make sure that I understand what's going on here. If we make the analogy to expression rewriting, can I think of this as being the definition of constants as opposed to sort of quantified variables?
Yeah, basically.
It's not actually, it's more, it depends what you use as a label. So you can actually also use patterns in labels, then they're going to be used as disjoint variables. So we have this special rule that if you have variables and labels, we just gather them all together and say, okay, all the labels should be all the patterns, all the variables and labels should be distinct.
Yeah, except that what you're saying is, which is a horrible situation, but one that we have seen before, we saw in the mathematics project, two x's are the same, but two x blanks are different. Is that correct?
Yes. In a way, labels would help us to mitigate this issue.
Exactly. Yeah.
Because we're imposing this additional condition that when we actually have like x and y labels,
right?
They should
as
be
opposed to just using it from the vertex names, with the convention that a literal vertex name is, I mean, somehow there's a sort of indistinguishable particle. I don't know what is the analogy. Is there a physics analogy? Two x's are just the same x, but two x blanks are distinct x blanks.
Yeah. I think in this context, all that's going on is that as I said, the vertices themselves are just some kind of background, and you're putting your information, your labels on top is really what tells you what the data should be. And again, I agree that this is conceptually indistinguishable from doing one edges, and it might well be that we want to go super homogeneous and just do one edges. But that's kind of the idea, that you want to express x and x, two copies of the same thing, two identical electrons, but they're in sort of two different points of space. So they want to live on different vertices. So at the level of the encoding in the language, they actually have to live on 1 and 2 as the vertices in the structure.
Let's keep going. I want to see what happens.
Wouldn't a more natural way to do that be to just have a multiplicity? To say we want to match x and x, but with strict multiplicity too, or something. I
mean, that can be an application, but I feel that it's more general, especially when you're doing pattern matching, as we are, to keep things as separate as possible. And if you want to do multiplicity, you can always do it after the fact, right?
Okay.
Let's keep going.
Well, maybe a few of these examples, because I think, or we can just go. I might show
some of the symbolic examples, because all I did was basically do an application of the hypergraph rewrite Paclet, which is to do sort of compositional algebra, like categories and things like that. And it was one of the projects that we were doing at the Institute to try and formalize several symbolic algebraic systems, and purely in terms of rewriting. And now we have the sort of demonstration that it already works. It has many things to tweak and to improve, but it's working. So if you want, I can.
Interesting, but let me just understand what this is. This is a multi-way system of some kind. What is it?
Yeah, that's we just applying the rewriting that we just tried to describe on this specific hypergraph, which is a semi-heap, Covers has a much more
And
examples.
I mean, that's going to be part of my, maybe I can go a bit more incremental and it will be clear what we're doing.
No, we just show this one because it has some maybe styles different from yours, right? So here is just it shows a bunch of things, so that there's a patterns, so that the labeled ages are also being propagated, so that the actual labels are in data. I think I have some leakage symbols again there. Where is it? Oh, that's right. It shouldn't be there.
I can show mine if you want. I have in my screen.
Yeah. Anyway, so it's just a multi-way system of rewriting, as usual.
Without
constructed.
Is there a merging?
Well, we can do contraction.
Yeah, but that has to take care of labels and some criteria.
Which means that you have, right now, in what you drew so far, you do not have hypergraph isomorphism, hypergraph canonicalization. It's just.
Well, I do have.
There is, but they are technically different because they are differently labeled.
You can do kind of different things with it, right?
Exactly.
I see.
You can turn them into some canonical graph and just edge list maybe.
Yes.
So that these things are all isomorphic, so they get contracted into one, and this one also isomorphic.
Exactly.
So
okay,
that's how we do it. So we have
this is very cool. So should we see Carlos's stuff?
Yeah. Let me show you. I'll just barrage a few examples, which are of the same kind. So let me share screen one. Can everyone see that?
Yep.
Okay. So I mean, this
You're
is just
a modern dark mode person.
Yeah. I like it as a Blackboard, sort of computational Blackboard feeling. So basically traditional category composition. So two morphisms FG composed to F composed G. And so if you want to, for example, check associativity, this I think is one of the main applications of this Paclet that I had the intention to develop, is to see algebraic axioms as emergent from rewrite properties of the system. And so in this case, you take this initial state and you apply the rewrite rule, and sure enough, you get this multi-way. I mean, these two final states are actually isomorphic, but the labels are different, and that's what has the algebraic information. So you have the associativity axiom there in that.
Hold on. Slow down. I'm not fast enough for this. Could you go back up to the top?
Yes.
Okay. So let's do commutativity first. You had the first picture, which was commutativity. Is that right?
No. This first picture, this is simply defining an operation, right? So this is defining what it means to compose two morphisms, two arrows, right? F, G, A, B, C.
And that to make a composed morphism there.
Exactly. So this is one example, by the way, in which you use this dangling vertices without edges as sort of contextual information that is relevant for the system. So yes. So then you choose your initial state carefully, and you could choose a longer chain if you want. But this is sort of the minimal case that shows some behavior, some algebraic behavior. And then you have A, B, C, D, and so three morphisms in a chain, right? And you basically just apply the rule, the composition rule, to this. So you can apply either to FG, so you get FG on the right, or you go to HG, so you get GH on the left. And then you apply again, because again, it's the same pattern, and you get a single arrow from A to D, but one is labeled by F bracket GH, and the other is right. So the idea that this is at the level of hypergraphs, unlabeled, is confluent, has some algebraic meaning. That's the entire sort of takeaway of the story, which is the cool feature that I would like to, create for the mathematical community, is like trying to replace axioms. This is going back to the subaxiomatic or pre-axiomatic sort of approach, where you replace enforcing axioms or listing them or enumerating them with simply spotting some rewriting behavior of the if your system is clever enough. In this case, it keeps track of labels and all this kind of business that we've been showing.
Okay, so hold on.
Sure, yeah.
So now algebraic equivalence becomes basically, you say that those two graphs are equivalent, although their labels, their sort of algebraic labels are different, and therefore you conclude there is an algebraic equivalence that you deduce from the equivalence of the graphs.
Correct. Basically, that's the idea. So you can state it in very, very precise terms by saying that you started with a simple hypergraph, right? This meaning there's no multiple. And then if you just look at the hypergraph level without the labels, you ended up with a multi-hypergraph, because that's actually confluent, but it has, if you're doing additive rewritings, you have two edges between A and D. So that way, that multiplicity allows you to spot. So the condition is like, okay, there might be a non-trivial algebraic statement here. And I say non-trivial because there are times where there's an algebraic statement where it's rather trivial, and that doesn't give you some interesting axiom like associativity. We find some axioms. So let me just, if this idea is clear, I'll show several examples, because they are basically the same, right? So the next is identity arrows, right? And this is, again, using the single element. Again, could be a one edge, could be a vertex, doesn't matter too much. So what it does is, takes the vertex and creates a duplicate of the vertex and then the identity arrow. So sure enough, you take some example, you have this, and you y and x, and it creates x here on the right, and it creates y here on the left. So this is just an example. Now, so I want to show the interaction of two. Okay, so this is going to show the interaction of two such rules. So in this case, the dagger is just flipping the orientation of the morphism, right? So if you take just a normal V pattern, so FG, right, ABC, then you can apply both composition and dagger, right? This is the usual exercise that people learning categories do. And you apply it in all possible ways, right? So you first compose F and G, and if you are on the leftmost side, you just leave in composition line in some sense, and then you apply some daggers here. So the idea is that here in this second state, you spot AC with a morphism in the right direction and B standing alone, and you spot that here down as well, right? So in the bottom right, and there you spot the involutivity property of the dagger, this anti-homomorphism property that basically says that dagger of FG is G dagger F dagger, right?
Yep.
Again with the same idea. So another example, and this is the only example that I've discovered properly with this method, with this approach. This is the first time that we can do it computationally, but just by hand I discovered this case a year ago or so. Is this what's technically called a semi-hypoid? So there's two ways to encode a semi-hypoid. You can do it either with arrows or with triangles, or in fact higher order stuff, as long as you have two sizes. So with arrows, you basically have a diagram. So now this is the rewrite rule. So the diagram is, arrow in one direction, arrow in the opposite direction, and then arrow in the other direction. So it's basically this non-circulating, and sort of the dominating direction wins, and you get a composition FGH from beginning to end, right? So if you take your clever initial state that has this shape, so it's basically a chaining and alternating chain of arrows, and you apply that to this, what you end up is, sure enough, you have 3 hits in this chain of the rule, and then those 3 hits produce again 3 arrows that are hits, and then eventually you end up with a single graph between 1 and 6. And then what's interesting is that you have one expression, one algebraic expression that derives from it, which looks like associativity. You're moving the bracket around because these things are sequentially ordered, but when you go in the middle, precisely because there's this flip of the arrow, there's this twist of the elements in the associativity property. That was identified in the 50s as something called a heap, and it has its own algebraic history. It's quite a weird ternary algebraic structure. That was not. Anyway, same pattern.
Okay,
can be
hold on. So, in standard sort of equational style axioms, I could write down some, we got a whole collection of them in the language, for example, of these collections of equivalences. So are you saying that any such equivalence can be compiled into a graph rewriting, into some, like, for example, let's say, well, like I have this, minimal axiom for Boolean algebra. Are you saying that there is a graph rewriting that is equivalent to that minimal axiom?
My feeling is that that's true, but I haven't proved it, and I don't know exactly.
So if that's the case, just so I understand, in the usual way, there's a law of inference that allows you to go from one sort of equational statement to another. And that law of inference has, you'll have a multi-way graph based on applying those, using the law of inference in lots of different possible ways. That will get you a collection of equivalent expressions. But in other words, if you, well, it's right.
It's a slightly different point of view, because the equational, it's also can also be seen as rewriting and manipulating expressions, but this is somehow deeper in the sort of closer to the machine code, or some sort of way where you're somehow just letting the system do its thing. And if you're interested in recovering algebraic information and equational information like we are used to as mathematicians, then you can spot for just rewriting properties of the system. In this case, this confluence where there's multiplicity and you might have different labelings, and the labelings, the actual information, the algebraic information is actually in the labeling, not so much in the rewriting. The rewriting is just, it's doing what it's doing, right? It has a life of its own.
Okay, so what you're saying is, in this case, the emergence of an equality is a consequence of confluence.
Correct.
There would be no equality without confluence.
That's right. That's right. That's the takeaway.
And the things that the algebraist is paying attention to are merely the labelings.
Correct.
That's right. What's being, go ahead.
Can I interrupt at this point? So,
yes, please.
So first of all, the answer to your previous question is yes. The minimal axiom for Boolean algebra could be represented in this way, because all that's being done here is effectively just manipulation of. I mean, this is just an operationalization of the concept of commutative diagrams. So the point is actually that there's no need for multi-way structure. You can do exactly the same thing with a single-way system. So if you go back to the associativity example, what's really happening is, so these happen to be destructive writes, or destructive rewrites, and that's why you need a multi-way system. But if you did the non-destructive case, so if you had a rule that said, if you've got one edge that goes from X to Y, one edge that goes from Y to Z, and you replace that, you don't do a replacement, but you just add an additional edge that goes directly from X to Z. Now you've got a rewriting rule that effectively operationalizes the property of the operation of taking a transitive closure.
Yep.
And then the condition that all multi-edges in that graph are equivalent is the statement that the corresponding diagram commutes. And there's a universality theorem that says any algebraic equation can be represented as a commutative diagram.
Okay, hold on. So there are multiple pieces here that I'm not very adequately familiar with. So Jonathan, commutative diagram is, you've got a bunch of morphisms, and you've got, it's the state. Walk me through how this works. You're saying that
the point is, in a commutative diagram, all you're saying when you say that a diagram commutes is effectively that all paths, if you take any pair of edges, all paths between those edges are equivalent, yield equivalent morphisms on composition.
Yes.
Wait a minute, between those edges or between those vertices?
Between those vertices, all paths between those vertices. Oh, sorry, yeah.
All paths between those vertices. So that is a general sort of category theory kind of thing, that you've got these two, well, right. Actually it's not, that you've got these two objects, and you've got morphisms that go from one to the other, and they're different ways they're kind of different sequences of morphisms that get you from one to the other. But since you're going from the same object to the same object, that means that those different morphism paths must somehow be equivalent. Is that right?
Right, exactly.
That's right. Yeah.
And so the point is that, anything that you can, this is actually how categorical works internally, right? So it's all just graph rewriting underneath, or any commutative diagram can be constructed from some elementary graph rewriting rule. And as I say, you don't actually need a multi-way structure. You can do everything with a single-way system, because of confluence guarantees and other kinds of things. And then the point is that anything you would represent with the algebraic axioms that you derive from a commutative diagram, you can then compute in a directly algorithmic way by just saying, well, show me all, compute the transitive closure, show me all of the multi-edges, and then let me just make an equivalence between all pairs of multi-edges.
Yep.
And I can show an example in Categorica of how this works in a second, but
okay, but I understand this. So that's basically,
that's what's going on. And so the point is, so long as your rule for how morphisms can be composed, or how morphisms can be generated from the underlying quiver, as long as those rules can be general enough, you can represent any algebraic theory in that way, including axiomatizations of Boolean algebra.
Yeah.
Okay, but the way that you would lay down those axioms. So, I mean, your initial picture here.
Yes.
What would that conceivably look like for a non-trivial? I'm confused how you encode. I mean, the axiom is an equivalence between one algebraic object and another.
Right, right. And so in the scheme that I was describing there, in the sort of commutative diagram scheme, you would have a rewriting rule that introduces new edges to this in accordance with some rule. I mean, so in this case, it would be, if you've got, as I say, if you've got an edge that goes from X to Y and you've got an edge that goes from Y to Z, you replace it with one that goes from X to Z. That would be the case. So that's like that's the applying transitivity thing. And then you just apply that rule everywhere it applies until you reach a fixed point. And then once you reach that fixed point, you just apply equivalences between all of them, between all the multi-edges.
What's that?
So I just made what I think Jonathan is describing, right? So you're adding the edges. I think
exactly. So if you apply that rule now to that thing, you don't want its complete multi-way structure, because using a multi-way system is just going to complicate things. But you'll see there
some nasty error. I think there's some memory that was.
You have A assigned, I think.
Yeah, I have A assigned for sure.
That's why formal symbols are useful.
Okay. Let me call it X, Y, Z.
You just clear A. Whatever.
And using a capital D is such a disastrous idea. But anyway, what happened there? Oh, okay. All right. So now interpret this.
So you'll see there are a bunch of multi-edges that have appeared. And so the point is, if you run this system until you reach a fixed point, and then you just impose equivalences between all multi-edges, that corresponds to the statement that the original diagram commuted.
I understand. I'm trying to just work out, how does this relate to sort of the entailment cone stuff Nick might understand from the Metamathematics project, or maybe Jonathan also understand. Maybe you all understand this. How does that, I mean, this is like making an entailment cone, isn't it? But it's just doing it in a slightly different way.
Yeah, it's in some sense, it's sort of like hands off, that you specify the compositional rules and you let the system evolve.
Let me make a comment on that. I mean, to me, substitution is a very natural thing to do with a symbolic expression. Okay.
Yeah.
But it is realistically at some level a meta logic. In other words, I think none of these things, it's like modelless models. I think nothing gets away without having some meta logic. You can argue your meta logic is more natural than some other meta logic, but I think you always have to have something. Or am I wrong?
I think, I don't know if this answers not your question directly now, but your comment earlier, but the picture that you have in mind, by the way, which is the title of this thing, chemoid, weird word, is that instead of, so a category is an example of a chemoid, because you from the perspective of, like Jonathan was saying, that you have like a quiver, you basically have a bunch of rules that tells you what to do. And in this case of a category, simply you compose like this, and you have units like this at the bottom, right? And then it's more about, okay, now I have to specify my initial states. And there are many perspectives you can take. You can take the sort of commutative diagram perspective, or you can take the sort of pure rewrite perspective, or just set theoretic perspective with source and target maps and all that kind of stuff. But at the end of the day, once you specify those two pieces of information, the rest sort of follows, right? And the question is, how do you encode the conditions that you impose on how those operations work? And traditionally, you would impose something like associativity, and in many usual presentations of category theory, they would literally state it, like in an algebraic theory, they would say, whenever you have this situation, you have to equate these two things. But with different perspectives, you get different formulations. So this is not something completely revolutionary. It's just saying this is a much more rewrite.
Yeah, sure, which is very interesting.
Yeah,
I'm just trying to push back on the idea that there is something. I mean, there are multiple ways to do sort of natural seeming rewrites. For example, I think substitution is a very nice structural way to do it. What you're providing here is something that is, I'm still trying to wrap my head around exactly what's going on here. I mean, can you scroll down for a second? Can you get to a fixed point there? Did you reach a fixed point? If you evolve for another step, will you get to a fixed point?
I think it's going to keep on adding multi-edges because it's going to spot the pattern over and over again. So it's going to.
Yeah. So will it ever reach a fixed point?
Not explicitly in this case.
It's not removing it, right? It
not,
doesn't
yeah.
remove the pattern, so it
Right,
always will match.
yeah. But it will reach a point where it's no longer connecting vertices that were previously unconnected, which is, I think, the thing that matters.
I see. So if you take those hypergraphs and you
hell, if you run something like this, you can do it.
Try it.
Just with
Pick it up
old
from the chat.
graph rewriting code.
Carlos?
Yep. Whoops.
Well, probably doesn't matter, but okay, what did that just do?
Is that what you wanted to see?
Okay, maybe do states plots list if you want the diagrammatic representation.
In the last argument of the Wolfram model.
Yeah, sorry, the property at the end.
Here.
Plots.
Yeah, just make it plots,
Okay.
states plots list. Sorry.
By the way, those shadowing messages, it would be nice to somehow avoid that. Anyway, okay, fine. So now what do we see?
So this is structurally what's happening, right? So you've got three morphisms laid out end to end. I've got a rule there that just, anytime you've got two of them that share a domain and a codomain, you just add a new edge between them, a new morphism between them. So now you end up with a bunch of multi-edges, and then the statement of associativity is the statement that all those multi-edges are the same in some sense.
Yeah.
Right. So this becomes a complete hypergraph in some sense. At some point, it becomes a complete hypergraph, and then you can read off from getting from A to B. What are all the different ways to do that? If you did sort of I don't know what they're called, some kind of tracing graph thing where you keep the labels of how you got that equivalence, so to speak.
I mean, I'll let Carlos get to the end, but in a minute I can show an example of this, of how this works internally within the category theory framework, because it is just kind of graph rewriting internally.
Yeah.
Sorry, go on.
Go on.
Oh, sorry. No, all I was going to say was, so in relation to your previous, slightly more philosophical question, the way so you're right in a sense that, you always need some kind of meta logic, right? You need there's some ambient thing in which you need to immerse the rules, which is, in this case, you're immersing the rules of mathematics inside WL, which is, the thing in which you then enact the substitutions.
Right.
I would say it's a little bit different from the entailment cone stuff, because this is one of the reasons why. Okay, for me, this is one of the appealing features of category theory, is that it gets around one of these, what in my opinion is a kind of core philosophical confusion, which is, so suppose you want to, suppose you want to generate a multi-way system for group theory, right? What would that mean? So there are many different levels in which you could do that. One is you could say, well, let's do the universal algebra thing, right? Let's start with the axioms of a group, and let's take some statements as the initial condition. Let's apply those axioms as rewrite rules, and we generate kind of true theorems in the universal algebra of group theory. That's one kind of multi-way. Another thing you could do is you could say, well, let's start with an element. Let's have the rewriting rules be applications of generators. And then the equivalence function is the application of relations. And then you've got a different kind of a more semantic multi-way system that effectively solves the word problem. And then you've got you've even got another level higher, which is you could say, well, let's have each state vertex be a group. And then let's have each morphism be, or have each evolution edge be a homomorphism of groups. And then each cyclic edge be an isomorphism of groups. And then we've got some multi-way system which represents kind of all the space of all possible groups. These are all different kind of possible multi-way structures.
I understand. And let me just understand this one, the one you just drew here.
Right. No, but the feature of category theory is that it removes this distinction. They are all the same thing. And so the point is that what's happening with these rewrites is not akin to application of axioms in the entailment cone sense. It's akin to application of generators, right? What you've got is an underlying digraph, which is the quiver, and then the elements of that quiver freely generate some category. By applying transitive closure, they freely generate some more complicated graph, and then the category is just what you get when you say, well, let's just apply equivalences between all the multi-edges.
Yeah,
I think I understand, but let me try that on the thing that you had from that Wolfram model evolution. In some sense, okay, one version of how you make a group is every node is a different word. In this case, the nodes are actually the elements of the group, and the different words correspond to different edges.
No, so in some sense, you want to ignore the existence of the objects entirely, right? You just want to focus on the morphisms. So
Yeah.
for the case of a group, the analog would be you've got a quiver which is just given by the collection of all elements of that, of the generators of that group.
Yep.
Then you freely generate some, then the graph that you get by transitive closure corresponds to all possible kind of combinations of those group elements. And then the relations are the things that then apply equivalences between those multi-edges.
Yes. I agree. How do we see that here?
Well, so in this case, you could treat this as like a 3-element group, right?
Yeah.
And I could read off. Could I read off equivalences between words by looking at which edges? If I were to label the edges, they would be labeled by words, and any 2 edges that go between the same nodes are equivalent words. Is that correct?
Yeah, we have some multi-edges there in the multi-way. In the multi-way system, like below. If you have a multi-way edges, multi-edges there.
What?
Where?
I think I'm still a little bit fuzzy here, but Jonathan's point about what category theory is doing.
Can I, Carlos, would you mind terribly if I just quickly shared for like 2 minutes, and then maybe this will.
Go ahead.
Yeah. I was gonna say, sorry.
Sorry. Yeah.
Can you say that again? I missed the sound.
Jonathan was just asking if he can share. When you should let Jonathan share.
Yeah. Absolutely. Go ahead.
Sure. Yeah, no, sorry. I'll hand back control in a sec. I just want to maybe this will help. Maybe it won't help, but just
take your time. I mean,
right. Okay.
Hopefully you can see a notebook.
Yes.
But okay, so if I do something like this, let's do H goes from X to W and I goes from W to Z or something. Okay, so there's a quiver, right? That's just a digraph.
Yeah.
So now if I were to take that, I generate this. So now, effectively, what's gone on internally is just a rewrite rule that's added an identity morphism to each object, and that anytime we've got a pair of morphisms that share a common domain and codomain, we just add an additional edge between them. So because of the because there are 2 routes from X to Z, we've got 2 different labeled edges here, right? That you can do I compose H or you can do G compose F.
Right.
And so
so what you're doing here is this is essentially a transitive closure of the thing above.
Exactly. And so then we can say commutativity equations, and all that that's doing is it's saying, well, let's find all the multi-edges, and then let's find the minimal set of algebraic relations that would be necessary to force all those multi-edges to collapse. And so then I can take this, I can say get those. So now commutative diagram returns true, and if I say reduced labeled graph, those will get canonicalized to a single thing. And so but then the point is, if I extended this, if I had, say, I don't know, F2 goes from Z, I don't know. Let me see if I can do this. Let's do Y to Q, and then let's have H2 goes from P to Q or something. Does that make any sense? It's probably the wrong way around. I don't know. Maybe that's sensible. Maybe it's not. Let's see. But anyway, okay. So there's let's get rid of that equivalence. But so there's an example of a more complicated thing.
Okay.
With a larger set of commutativity equations, but it's just the same thing that's going on internally. And so the point is that by setting up the underlying graph structure, by setting up the quiver in the right way, you effectively have fine-grained control over what element. So if you think of the morphisms here as being elements of some algebraic structure, like elements of a group or a ring or something, then by changing the quiver structure, and in particular changing which morphisms are, which of the edges are sort of which share vertices and which don't, you can change which elements of that algebraic structure are allowed to be composed with each other and which aren't. And so then, then the set of possible relations is the set of sensible relations in that algebraic structure is the set of possible equivalences that you can define between the multi-edges.
Yes.
And the point is, one of the reasons why category theory is so powerful is because there are these universality theorems that effectively say we can represent any algebraic structure in this way. That category theory is a strict generalization of essentially all of algebra.
Walk me through what that means in practice.
Sure. So the point is that if you were to take, if you wanted to represent a group or something, so if you're just generating a free group, then you want all elements should be able to be composed with each other. So you would construct a quiver in which all edges share, have at least one shared vertex between, in their source and their target.
Yep.
And so that would generate. So then the corresponding category would have the structure of a free group.
Okay.
So in the simplest case, so the canonical way to do that in category theory is just to have a one element category, or a one object category.
Mm-hmm.
But so, if just like one can enumerate axiom systems in the standard kind of symbolic, equational logic type thing,
right?
Can one enumerate? What's the corresponding enumeration of categories?
Well, so you can just enumerate directed graphs, and then, as I say, then you have some freedom. So then each one of those generates a free category like that. So this is the free category generated from this quiver.
Yep.
And then the point is that you have some freedom to make additional restrictions by equivalencing certain multi-edges. So you would start by effectively enumerating quivers, and then you would enumerate subsets of these additional algebraic axioms.
Okay, so let's say you enumerate quivers, you take transitive closures, you get categories.
Yep.
Then can you kind of scan over the different directed graphs and say what's the name of the algebraic object that corresponds to you're going to get out of the domain of ones which people have talked about, but I'm just sort of curious if you were to enumerate, because with axiom systems, for example, it isn't particularly natural. That is, the axiom systems that turn out to have been used in practice are not low-lying axiom systems. Do you understand what I'm saying?
Right.
So maybe that's not true for the category case. Maybe if we just enumerated directed graphs, would we scan over the commonly studied algebraic types of systems, or would we end up even very quickly getting things which haven't been studied and finding that there's just an obscure case that has been studied?
You would very quickly find things that haven't been studied. So this would be how you'd represent something like a group, as an example, right? So, so in this particular case, of course we've got two elements. Never mind. But okay, so this is very poorly laid out because it's not the categorical framework is not very good at laying these things out yet. But effectively, this is what you would see, right? So you've got so say you've got say you've got three morphisms that all connect one object. So you've got an F and a G and an H. So now you can compose those together, and any pair of them can be composed together because they all share the same object.
Yep.
And so you get associativity because it's from the fact that it's a category. You get identity from the fact that it's a category. And if you additionally impose the property that this diagram commutes, then every one of these every one of these edges has effectively an inverse, and so you get a group. And so a group is a one element is a one element category in which every morphism has an inverse, has a left and right inverse.
So Jonathan,
what's the significance of the fact there are three morphisms that you've drawn here?
This is the statement. This is a three-element group. If I drew another morphism, that would be a four-element group.
So how do you distinguish in this view? I think for the benefit of Stephen as well, how do you distinguish different three-element groups?
Yeah, that's an interesting question, right? So then you I think a hardcore category theorist would say that
the three element groups are the same. No.
The distinguishing feature is only in the algebraic the algebraic properties of what things are equivalent. Determining equivalences between those algebraic axioms is non-trivial, which is why I'm a bit hedging. But I think that is the philosophically that is the distinction.
Yeah.
But all isn't that an outside of category theory question? Those equivalences between the algebraic. Is that something isn't category theory blind to that? Doesn't it look in terms of category theory that all n element groups are the same?
No, really. I mean, not. It depends on what level, but not as a rule. So the point is that all 3 element groups would have the same underlying quiver. So
Yeah.
But if we take the free category generated by that quiver, there are many different possible. This commutativity equations list will not in general be empty. So there'll be many possible choices of equivalences between the corresponding multipliers, and each one of those choices corresponds to a different 3 element group.
Yeah.
As I say, that if you actually try and do this stuff algorithmically, which most category theorists don't, you run into this problem of how do you determine when two equational axiom systems are really the same thing, and that's not a problem I've managed to solve. But at least in principle,
it's undecidable in general. When are 2 equational axiom systems the same? Hopelessly undecidable, right? Because it's similar to.
But undecidability is fine because you can still define a semi-decision procedure. The problem is it's hard even to define precisely. Like,
Yeah. Okay. Well, for example, one thing you might do is ask, are all their models the same? But even that, no, that's hopeless too, because
no, exactly. But like, to take a simpler case, right? Imagine if you go back to your minimal axiomatizations of Boolean algebra. If you just show someone, 2 axiom systems for Boolean algebra that, for instance, potentially define different operators, right? One of them defines Sheffer-Stroke, but one of them defines, and or not.
And not, yeah.
And you ask, are these axiomatizing the same algebraic theory? It's very hard to figure out how you pose that as a decision question. It's clearly a well-posed mathematical question.
Well, let's think about that for a second, because that question is quite interesting. Because that question is similar to are 2 programs the same?
Yeah.
Anyway, Carlos, let me hand the sharing back to you.
I'm not going to move on from that question, Stephen, because. And thanks, Jonathan, for
start sharing again, Carlos. Yeah. Just the practical matter. Just start sharing your screen.
Sorry. Yes. You can see that, right?
Okay. Yes. Go ahead. What were you going to say, Carlos?
Yeah, I was going to say that. First of all, Jonathan, thanks for that, because what you showed for the category case with your functions there is precisely the sort of the philosophy that I have for this general case. What we're trying to do here is we're trying to push above the quiver structure, right? So we want to, in the same way that you have a quiver and you can generate, but as Stephen says, a transitive closure, we want to say, well, actually transitive closure corresponds particularly to this rewrite rule here, and taking quivers is already a choice because it's directed graphs in this kind of way. So what we want to do, a particular application of this Paclet and this kind of functionality is saying, well, what if we take all kinds of hypergraphs as potential diagrams to begin with, like the equivalent of a quiver, and what if we generalize transitive closure to other kinds of closure? And that's where the fish or I have this example at the very end, which uses this, basically this is, we're calling a tetroid, which is like a tetrahedron without one of the faces that rewrites the missing face with a triangle, right? So everything here is unordered. And so you can have similar situations where you rewrite and you get similar phenomena, right? And so the point, just to summarize, because that's really the point of this application that I was going to show, is precisely take what Jonathan has beautifully done with that functionality and try to generalize the quiver initial structure and the idea of associative closure and extend it and use sort of hypergraphs as a template for generality, which I think is the right generality that we want, and then discover things. And the thing is, we did rediscover this fish thing, this semi-hypoid, and to me that gives me, this is the operads, for example. It's also quite natural to encode operad, which is this sort of multi-category composition thing, and the fish in particular, right? So this to me is signaling that this potential for discovery, as Stephen was saying, that we might get into uncharted territory, but also charted territory that has been spotted. And this equation in the fish, this axiom was first listed in the 40s and 50s, and people have known about this, but it's very obscure. Almost nobody has heard of this, but it has been known, and it was rediscovered as an instance of this. And it was discovered by saying, I will start with, instead of quivers, I'll start with something like this triangular hypergraphs, and instead of composing by transitive closure, my equivalent of transitive closure is this sort of fish smashing, right? Where you get a fish, then you just put, head to tail triangle. And that's sort of the summary that I wanted to close it there. Maybe we can move on to the very interesting question.
So, okay, my question here would be, so one question is, if you enumerate by quivers, so to speak,
yeah,
and you ask the question, what do those different directed graphs, what algebraic theories can be represented by those different directed graphs? That would be an interesting thing to know, whether the ones that have been studied are ones that correspond to the simplest directed graphs, because it isn't true in axiom systems. In axiom systems, the ones that have been studied are pretty not low-lying.
I think that may be a less interesting question than it sounds. I mean, I agree. It sounds like an interesting question in the abstract, but effectively all algebraic structures that have been studied in kind of classical, what we might call classical algebra, pre-category theory algebra, corresponds to one object cases of more general categories. So the group case just now is groups are a one element groupoid, but there are also analogs of things. A monad is a one element monoid. A ring is a one element ringoid, etc. So the sort of the named algebraic structures will always end up corresponding to the single vertex.
Yes.
The things generated by single vertex quivers.
Yes, I would add, though, I completely agree, but I would add that the question of enumeration here, I think, becomes more relevant when you take the perspective of finding this phenomena as something that is a rewrite phenomenon, because formally you can say, if you can write it as universal algebra, there's this theorem that you alluded to, Jonathan, that tells you that you can actually model this in categories, right? But I think what's interesting here is that if you want to generalize, so for example, you wouldn't think of what is called semi-hypoids, right? In this context, where they are modeled with this fish or this sort of 3-arrow pattern, like the zigzag pattern that I call. I mean, those things are somehow primitive in the sense that you're taking that particular quiver model and you're saying the composition, the transitive closure works this way particularly. And so it's a matter of, okay, so that is semi-hypoids. Okay, that's that particular thing. So what are other hypergraphs or graphs that can take you to some interesting algebraic land? And that's the core question that I have in the background, which is, I think, quite related to what Stephen was saying, if I understood correctly, that if you try, and in fact my approach is going to be to enumerate to some degree up to some sizes all the possible small hypergraphs. That's part of the motivation to actually do sort of more classification, taxonomy of small hypergraphs, to be able to actually chart the sort of compositional structures that you end up with when you start with different sort of template diagrams, right? Because we know that you start with digraphs or quivers, you have categories and groups and groupoids when you have symmetry or maybe undirected and all these kinds of things. Those are examples of an otherwise question that is parameterized by what you take as your motif, right? What you take as your sort of starting motif, which is summarized in this kind of rewrite rules, right? So I think it's a very interesting question, and that's part of the. Okay,
so hold on. Let's see what will happen if you do this. So I mean, for example, there's decidability questions. Given a particular, how will you get sort of empirical evidence of undecidability in one of these systems? I mean, it's basically the existence of an infinite path in the equivalence between two things which will ultimately be equivalent will have an unboundedly long path to get from one to the other, I would suppose.
Actually, it doesn't have to be of unbounded length. You can have an infinite collection of paths all of bounded length would be the case where the word problem is undecidable.
Right.
A path of unbounded length would correspond to an infinite length word. Whereas the case for the undecidability of the word problem is the case where you have finite length words, but the number of algebraic transformations necessary to equate them is infinite. Which is the case where you have a finite length path. You have two finite length paths, but it would require kind of infinite multi-edge equivalences to translate between them. By the way, Carlos, I would say I do think this is really, really cool. And so if I'm understanding what you're doing correctly, so. Yes. The case of the sort of the graph rewrite version of for associativity that you showed above, which is the graph rewrite form of transitive closure. Yeah. This is really just this is encoding what in conventional algebra is just the application of left and right generators, right? If you do that in graph rewriting terms, this is what you get. The point that you're making, if I understand correctly, is that if you consider more general, so you're kind of generalizing what it means to apply a generator, particularly if you consider a higher arity algebra, some higher arity structure, then you could apply left generators, right generators, up generators, down generators, or whatever.
Yeah, all kinds of topologies. Yeah, exactly.
Right. And in addition to applying individual generators, you could also apply, you could have, you could apply one thing up and one thing left and so on. And so you get just a more general class of, what are ultimately just hypergraph rewriting structures. But then, then the argument is that all the same things that you would do in ordinary category theory to discover algebraic theories, you can do in the more general context. Which
exactly, and discover potentially different things or...
Okay, so let's take it another way. Let's say you're doing hypergraph rewriting, and that's your primary interest.
Right.
In a sense, you can view these things as an algebraicization of hypergraph rewriting.
Totally, yes.
So one of the questions there would be, we've got hypergraph rewriting. I mean, when we think about the physics project, for example, I have long claimed that hypergraphs are merely one representation of what's going on, and that there might perfectly well be an algebraic representation of what's going on, where the thing just looks like some complicated algebra. I don't know, maybe it's an algebra people have seen before. But my question is, if I pick a random hypergraph rewriting process, does this provide a way? Okay, several questions. One, do you get sort of exactly solvable hypergraph rewriting models out of this because they correspond to some algebraically reducible thing? Two, is there given an arbitrary hypergraph rewriting system, is there some kind of algebraicization that this implies?
Okay, yeah, I think interesting answers to both. In the first case, if I understand correctly, the answer is no in general, but that's interesting because you get, these are examples in which you do get
sure, I understand. Right, in the case of cellular automata, for example, there was a hunt for multiple years of are there cellular automata that are exactly solvable? For example, using relations in number theory, for instance. There are rather trivial ones that use additivity and are exactly solvable, but nothing was ever found that would use, I don't know, some weird Möbius inversion formula or something to be solvable. So the question is there in hypergraphs, before you get out of the atmosphere into where you can't breathe anymore and it's all irreducible, are there still other forms, other than the trivial things? Are there sort of exactly solvable cases? Like in partial differential equations, for instance, we know there are integrable systems, which are a sparse set between sort of linear systems and the nonlinear mess. But so the question is, are there similar things here?
Well, the hope is that there are, and in part, the reason why I included this tetroid example in the end is because this is a very, very likely example, but we still have to actually. So maybe let me flesh out this point because I think it will make clear what I mean. So this particular system the algebra that comes out of this has been studied by someone called Bhattacharya Messner. There's a paper from 1990 that discovered this association scheme, and they basically postulated that the operation is like this. You have a tetrahedron with 3 triangles, and then you basically rewrite the missing one. And the idea is, okay, so so everyone knows that this is non-associative in the conventional sense. It's a ternary operation that is non-associative in the conventional sense. So the question is, does it satisfy some form of associativity, right? That's a basic question. So the first thing you might want to spot is, can I find, so in my perspective, in this sort of rewrite perspective, you say, well, can I find an initial state, I hook up an interesting looking hypergraph, so that I apply the rewrite rule and I get something like confluence like before. So you can actually do it in quite a trivial way. So you can, this is basically, this looks like a mess, but that's basically a tetrahedron where you're placing a tetrahedra on each of the 3 faces, right? And so you surely enough, you apply the rule and you get obviously a confluence system because you're doing, collapsing each of the horns independently. And sure enough, you get to a single place. And if I had all the labels, those would be different labels. They are different sequences. Now, when you actually look at what you are doing in the algebraic expression, effectively what's happening is that you're doing, you have a bracket that takes three inputs, right? So effectively what you've done is you've done A, B, C, and then you've done whatever 1, 2, 3, and then you've done X, Y, Z, right? So in some sense, you've not done anything interesting in algebraic, right? So indeed, this confluence property actually is connected to the fact that you can take any order of operations there. You can operate ABC or XYZ, and then the other, and so on, right? So it basically just says, well, if you were to make this into a traditional algebraic system, you have some freedom in the order, in the sequence of contracting brackets or operating your elements, and ultimately there's a single output, right? So in this case, this property hasn't spotted an interesting equational axiom, right? So my hunch is that I didn't find a clever enough initial hypergraph. So that's where the enumeration or the systematic.
Yeah, right. You just have to try it.
Right.
Right. That's the only way to find it out. You will
Exactly.
never be. One will never be clever enough to do this. One will
Exactly.
enumeration is the right way to do it. But the question I'm asking, I mean, I'm just trying to understand the strategy here.
Yeah.
There's several strategic endpoints here, it seems to me.
Yeah.
One would be.
Can I answer your second question, or you want to?
Please. No, go ahead.
Yeah, the second question I feel it was part of the. I mean, it's a bit late, and I had another notebook where I expanded a little bit on that point. But there's a very obvious way to algebraize a hypergraph rewrite system. In fact, let me just bring up the notebook.
Yeah, please go ahead.
So this is the perspective of hypernetwork theory, basically, right? So or what I'm calling hypernetwork theory. I haven't heard that said in many places. So the standard story, I'm just going to recap very briefly. Standard story is you have graphs in which, your adjacency property basically says, is 1 connected to 3 via some 2, some intermediary 2. And we all know that the adjacency matrix of a graph has the algebra of the adjacency matrix of the graph has something to do with paths in the graph, right? So basically what I demonstrate here is, I mean, by the way, this is using the same Paclet function, so this is not a particular case. So what I want to do here is, okay, let me actually show the algebraic part first. So I take adjacency hypermatrix, I take the square A times A, and sure enough, if my initial state is this, I should get something that looks like, the 2 paths that I can connect of length 2, right? So the demonstration here is, okay, we know the algebra, this is traditional algebraic graph theory, but the question is, can I make that into a fully rewrite construction? And the answer is very simply yes. You can do this sort of one pass rewriting, which means that you're basically just adding the single application step, but all at the same time, right? So that particular rewrite algorithm corresponds exactly to taking the square of the adjacency matrix. Of course, that's a when you look at the square of the matrix algebraically, that's a very special construction. It's A squared. It's basically the only thing you can do if you only give me one element and I have a binary operation. But if you look at the rewrite side, and this is what excites me, this is a very special construction that you've done. You could have done a myriad of other things that don't have an immediate interpretation algebraically, but are nonetheless perfectly well defined for the rewrite perspective, right? So there is a clear embedding, so to speak, of the algebraic description of graphs in the rewrite world. You just have to specify rewrite procedures that implement the algebraic structure. Sure. So conversely, you can say, well, if I find some particular algebraic behavior, particular rewriting behavior on this side, I might actually get some algebraic behavior when I do the adjacency sort of dualization of the.
Well, I mean, my expectation would be general graph rewriting is vastly more general than anything you can capture with algebra that anybody's ever seen before.
It looks like that, definitely.
Right.
Yeah. Definitely.
So, I mean, and then the issue is, as I was saying before, when do you get out of the atmosphere, so to speak? When do you get to the point where everything's irreducible, you can no longer say anything? And is there a waypoint like integrable differential equations, for example, where there is an exactly solvable case that is intermediate between the rather trivial cases that one already knew and the cases where one can't do anything? And that would be, my guess would be that there are such situations with hypergraphs. And that would be kind of interesting to find, because it would provide one with a, another model system that's non-trivial. I mean, I've, spent too many times, I've ended up with a grid graph as, this or that example of what happens with hypergraphs.
Right.
That's just one. I mean, from a strategic point of view, that would be one thing that would be nice to have, is a, at least in the history of statistical physics, exactly solvable systems like the two-dimensional Ising model, for example, have been very useful. And so, having an exactly solvable hypergraph model would be a very useful thing, I think.
Yeah. By the way, what do you mean by exactly solvable here in this context?
Oh, I don't know what I mean. I don't know. Nobody ever knows what they mean by that. It basically means you can compute things without having to just computationally irreducibly run stuff.
I see. I see.
In the two-dimensional Ising model, you can compute all the correlation functions just sort of by using algebraic formulas.
Right.
Whereas in 3D, we only know how to do it by doing simulations.
Right. I would say my initial answer to that would be that it's precisely the kind of the motivation of this entire effort, which is that if we do have some criteria of what rewrite systems are interesting and what rewrite systems do, the kind of things that we're interested in particular, the confluence with different labels and to spot algebraic axioms and things like that. So the idea would be, the hope would be that once you start charting this unfamiliar territory, it doesn't have to be huge. It's just unfamiliar. It's small but unfamiliar. Then you have this criteria of, okay, in this context of categories or groups or rings or whatever, this particular properties that I'm familiar with, like associativity or distributivity, correspond to this particular rewrite property, most commonly confluence and so on. And so the idea is to go exploring and then have those as some kind of templates that you can compare and then try to, because surely you will find things that are just very wild and they don't do anything.
No, right. So I mean,
yeah.
Right. There are ones where you will be able to say things and where you will be able to map them onto sort of some existing mathematical knowledge, and others where you will not. And so finding which ones are, I mean, it is non-trivial to find out whether they map onto existing mathematical knowledge, unless this is a really great representation, sort of knowing that the thing has some, I mean, that's why it was non-trivial to solve the two-dimensional Ising model or something, to map it from being an Ising model to being something involving, I forget what, hypergeometric functions or something like that, which is what the solution comes out in terms of. I mean, anyway,
can I make a remark? So
yes, please.
Okay, so I suspect that what you're referring to as exact solvability is precisely what Carlos is doing here with these, with this algebraicization of these rewrite rules, right? So that effectively, if you can take a hypergraph and you can represent, or a hypergraph rewriting system, and you can represent the equivalence structure, like like for the case of associativity here, purely in terms of kind of elementary algebraic operations on, say, its adjacency hypermatrix, then I suspect that's kind of the analog of what you're describing.
I agree. Absolutely, okay. Indeed, yeah.
However, it is important to note that is of a fundamentally different character to something like exact solvability in a cellular automaton, or indeed in an Ising model, because this is exact solvability of the equivalencing, not exact solvability of the evolution.
Yep.
Well, fair enough.
So because with a cellular automaton, the equivalence function is trivial. I mean, you don't really worry about it for the case of a deterministic CA. So when the algebraic work that you're referring to, Stephen, is stuff where people are saying, okay, predict, can I have some formula that tells me in 100 steps what the CA register is going to look like?
Yeah, that's right.
Whereas that's not really a concept that appears. If you consider the algebraicization of hypergraph rewriting systems, that's not really a concept that exists. You don't have in algebra a concept of like, show me what the words of this algebraic structure will look like after 100 generator applications. That's not really a question that people ask.
Well, except you've got these pictures that show going from one state to another state to another state.
Right. But my point is that even if there were some notion of exact solvability, it's unclear the terms in which one would express that. Because conventional algebraic structures certainly don't do that. Exact solvability, I think, is easy to define at the level of the state equivalence function. I think there's also something else going on at the level of the state evolution function, which has no obvious analog.
Fair point. Yeah, fair point. I'm supposed to go to something completely different, but go ahead. Just a few more minutes, and then I really got to go.
Let me add one extra thing, which I mean, I think ties up things nicely, which is this question of whether some of these systems map onto existing mathematical systems or non-algebraic structures and things like that. This is actually something that we have been thinking about at the Institute recently, I mean, in the last, I don't know, couple of months, where actually the reason why we started developing this hypergraph stuff is precisely because it allows us to draw diagrams that are extremely general and they can encode all sorts of formal systems. And we, I had fun some afternoon just translating all kinds of SK Combinator stuff into the hypergraph rewrite rules, so I could, convince myself that these are sort of a template that you can use to quite generally express things. And so one of the questions, that long-term questions that are beyond this particular searching for behavior of rewrites is that, exactly what you mentioned earlier, Stephen. How do you determine that two things are in fact the same, or what we called it in this context? How do you decide that something is emulating something else, right? How do you decide that that system is actually
an important problem?
Exactly, right?
That's an important and not. I mean, nobody knows really when you say this register machine can be emulated by this Turing machine. Nobody has a good sense of what the distance is of some kind of distance metric of that emulation, which is essentially a Rullial space distance of some kind.
Yeah.
And we don't know how that works.
Exactly. So one of the main reasons why I pushed a little bit to go into this hypergraphic approach is that hypergraphs have quite a natural combinatorial structure, and so if everything can be expressed as some form of labeled hypergraph system, then you have quite a bit of machinery to actually, you take if SK Combinator is a particular hypergraph rule rewrite and Boolean algebra is a particular hypergraph rule rewrite, as we were doing in the beginning when I joined the Institute, then you can clearly see that, if these are expressed as hypergraph rewrite rules under the same footing, then you can just apply some, hypermatrix entropy measure to determine, distances between these things, and you have some preliminary approach to the difference between the two systems, and you find obviously that one is, much more parsimonious, and the other is much longer in computing time, right? In the computing steps. So it's definitely one of the advantages.
Well, I mean, the question really is, we already know, like in Wolfram language, tree-based rewriting. We already know, admitting the fact that in that case, code and data are a little bit different. I mean, they can be represented as the same thing, but they are applied differently. And I don't know whether that works. It does work somewhat differently. And that's why this whole question that we were discussing earlier about hypergraph rewriting rules versus hypergraphs themselves. And Nick was kind of showing some differences between the way to think about hypergraph transformations and individual hypergraphs. But in a sense, we already have one universal representation, which is just symbolic expressions. But that's a case where we have a bit of fancy footwork because we have things like patterns versus non-pattern expressions and so on. And maybe with hypergraphs, there's less fancy footwork to do. I think there may very well be.
Do you mean?
Go ahead.
Do you mean that they are somehow more parsimonious
no, they don't have as much. Look, in the case of transformation rules on symbolic expressions, you have to have the concept of pattern variables, for example.
Right.
And you have to have also some sense in which, well, the rules aren't necessarily different than the expressions themselves. I mean, I had a whole discussion about that in the MetaMath project, that you can apply rules to rules and all this kind of thing. But go ahead, John.
Go ahead.
But surely, I mean, even in the hypergraph case, you surely still have to have some notion of effectively which hypervertices you're universally quantifying over and which are treated as constants in your rewrite rules, right? That doesn't get you out of the pattern problem. Maybe.
I'm not sure about that, because I think you could decorate. I mean, you could probably do this in the same with pattern variables, but I mean, you can like label a thing as a constant by decorating it with sort of some number of different numbers of self loops, that type of thing. I mean, it's a bit of a hack, but maybe you can do exactly the same thing with pattern variables. I'm not sure.
Yeah, but, I mean, that's the analog of saying that I can just wrap a pattern in arbitrarily many heads.
Yeah, that's probably right. Yeah, that's probably right.
Yeah.
So I mean, the question then is, I think the basic point is, everything has to have an evaluator at some point. Without an evaluator, nothing happens. Is that a fair claim? I mean, in other words, whether that evaluator is saying hypergraphs are transformed or whether it's saying expressions are transformed, it's, well, and this is what's confusing about the mathematical case versus the physics case. You know, in physics, the application of the evaluator is time, you know, measures time. Whereas in mathematics, you merely discuss equivalences independent of time, in some sense.
Well, I think my approach to the quote unquote emulation problem that we mentioned before was precisely to try to make mathematical equivalence more time-like, unintended maybe. So
yes,
so that was part of the game, I guess, that you were trying to make mathematical equivalence into something that is in a sort of causal structure or in some kind of rewrite flow, and you can take time-like measures or you know like observer-like measures. I mean, that you have
right.
this.
Hey,
this kind
listen,
of
I've now just run over 2 meetings, so I really have to get going here. But this was interesting and a good. I hadn't had a chance to check in on any of this stuff for a really long time, and so this was really good to see. Jonathan,
Nice.
any last comments that you might have?
No, I think this is really cool.
Thank you very much for your comments, Jonathan and Stephen. It was very helpful. Thanks.
All right, we'll see you
thanks.
guys soon, and thanks to folks who've been joining us on the live stream. I've got to run off. See you later. Bye, guys.